All right, I think we can start again. Right, about the adjusted R square. So in the case where we need to make decisions on whether to add one more independent variables into the model, we cannot use R square because of its problems. All right, so in that case, we must use another coefficient of determination, that is the adjusted R square, and we denote it as, all right, R square bar. Okay, and R square bar is just the coefficient of determination with the adjustment for the sum of square of the for the degree of freedoms of the sum of square. Okay, look at this. You can see that R square bar, right, it's just the coefficient of determination, that is 1 minus n uh, 1 minus r at s divided by t at s. Okay, with the adjustment to the degree of freedom of those sum of square, which is n minus k minus 1, and this one is n minus 1. Okay, so this is our adjusted R square. Okay, and what else? K is the number of independent variables in the model. Okay, and n is the sample size. Adjusted here mean adjusted for the degree of freedoms of the sum of square. All right, and actually because of the adjustment, we have a relationship between R square and the adjusted R square, which is okay. So because R square here, okay, R square bar, the adjusted coefficient of determination, is equal to 1 minus, what is it? We have R at S, okay, divided R at S multiplied by n minus 1, okay, because this one is in the denominator of the denominator, so we can put it in the numerator, and divided by, what is it? T at S times n minus k minus 1. All right, so it will be, what is it? 1 minus r at s divided by t at s, and r at s divided by t at s is equal, also we have r square equal 1 minus r at s divided by t at s. That's why here r at s divided by t at s is equal to 1 minus r squared, okay, and times n minus 1 divided by n minus k minus 1. Okay, so this will show the relationship between R square and the adjusted R square. Okay, the adjusted R square is equal to 1 minus the R square and multiplied by n minus 1 and divided by n minus k minus 1. All right, so because of this, if we know the coefficient of determination of a model, then we can calculate the adjusted R square of that model, and vice versa. If we know the adjusted coefficient of determination, we can calculate the coefficient of determination R square. All right, that is the relationship between R square and the adjusted R square. Okay, here it is, right? Where n is the sample size and k is the number of independent variables in the model, right? And we have some properties of the adjusted R square. The first one, when k is greater than 1, then R squared, the adjusted R square will be less than the coefficient of determination R square, and they are smaller or equal, and r square is smaller or equal to 1. Okay, and because the number of independent variables in the model is always is it is usually greater than 1. Actually, let me see this again. Because k is greater than 0. Okay, actually it must be because k is greater than 0. So r square bar is always smaller than r, right? R square, sorry. Okay, I must correct this. I think because k is always greater than 0, then we will always have r square bar, the adjusted coefficient of determination, is smaller than the coefficient of determination. Okay. Also, look at the formula of the adjusted coefficient of determination. We can see that it penalizes the model with a larger number of parameters to be estimated, which means that it penalizes when we add one more independent variables into the model. Okay, as you see, there's some bad effect when we add more independent variables into the model. So r square bar, the adjusted coefficient of determination, will also penalize the model when we add one more independent variables into the model. Okay, if r square is always equal to greater than 0, which means it is a non-negative number for a model with an intercept, then r square bar, the adjusted r square, can be less than 0. Okay, sometimes when r square is so small, okay, is equal to 0 or is close to 0. Okay, so our adjusted coefficient of determination can be less than 0. Okay, right. And the adjusted coefficient of determination is used to compare the compare the goodness of fit between the models with different number of explanatory variables, but they should have the same. They have the same dependent variables. Okay, it is used to compare the goodness of fit between models with different number of independent variables, but those variables must have the same dependent variables. Okay, for example, if this model has the dependent variables as y, that model will also have the dependent variables as y, not the logarithm of y or y squared. Okay, all right. And there's another case. There's another case that we use the adjusted coefficient of determination. That is when we want to add one more independent variables into the model. We will add, okay, one more independent variables into the model if, okay, if when adding that variables, it make the adjusted r square to increase. Okay, so now look at the adjusted r square. We have the adjusted r square here. The adjusted r square, which is equal to what? 1 minus r at s divided by n minus k minus 1, and also t at s divided by n minus 1. Okay, and here r square is equal to 1 minus r at s divided by t at s. Okay, so last time we say that R square is a non-decreasing function of a number of independent variables in the model. Okay, and it will not change only for the case when the estimated coefficients associated with the new added variables is equal to 0. Okay, so what will happen to R square? Okay, now answer me. What will happen to R square if we add one more independent variables into the model?
R square will be unchanged or increase.
Okay, in most of the case, okay, in most of the case, you can see that R square will increase. Okay, okay, it will not increase or mean that it will not change if the estimated coefficient associated with the new added variables is equal to 0. Okay, and that case is very we will later, okay, we hardly see the case when the estimated coefficient is equal to 0. So most of the time, okay, most cases we will see that the R square will increase when we add one more independent variables into the model. Okay, now the change in the value of the coefficient of determination is because of the change in which element. Okay, here is the formula to calculate R square. Now, when we add one more independent variables into the model, we see the change. We see the change in R square. So that change is due to what? That change is due to the change in what components? The change in what, in which components or what element of this formula cause the change in R square?
IS.
I at S, yeah, right. You can see that T at S here. T at S here is the sum of our observed value of Y minus the sample mean of Y. And this value is independent of the model. Okay, you can use any models to explain the variation in the value of Y. Okay, but the TLS here is not changed. Okay, as long as your dependent variables stay the same. All right, so this one is not changing, and the change in R square here is due to the change in IS. Okay, so when you add, oops, so when you add one more independent variables into the model, it will cause IS to increase, to decrease. It will cause IS to decrease, and it make R square to increase. Okay, all right. So what will happen to the adjusted coefficient of determination when we add one more independent variables into the model? There will be two effects on the adjusted coefficient of determination. Okay. Now, what will happen to the adjusted coefficient of determination when we add one more independent variables into the model? What is it? When we add one more independent variables into the model, which components will change? Which component of this formula will change?
K.
Okay, all right. So K, what happened to K?
K will increase by 1 unit.
Yeah, okay, so K increase when we add more independent variables into the model. So when K increase, what happens to the value of the adjusted coefficient of determination?
It will increase as well.
Is it when K increase?
No, it will decrease.
Yeah, it will decrease, right? The adjusted coefficient of determination will decrease in this case, all right? And also R square increase, right? Okay, when we add one more independent variables into the model, R square will also decrease. And what will happen to the value of R square bar, the adjusted R square? What will happen to it? When IS decrease, what happened to the adjusted coefficient of determination?
It will increase.
Yeah, it will increase, of course, right? All right. So you can see that. All right. There are two effects on the value of the adjusted R square when we add more independent variable into the model. Okay, one make it decrease and one make it increase. So the value of R square, the adjusted R square here can increase or decrease. Okay, it depends on which effect is larger. Okay, so it depends on whether the positive or negative effects is larger. Okay, so it's different from R square. For R square, when we add one more independent variables into the model, then R square will also increase. Okay, but for the adjusted coefficient of determination, which which penalize the adding, okay, the adding of more independent variable into the model, it will increase or decrease depending on which effect is larger. All right. So we will add, okay, here when we can use the adjusted coefficient of determination to make decisions about whether to add one more independent variables into the model. So if adding that variable make R square, the adjusted R square increase, and also the coefficient associated with that new independent variables is statistically significant, then we can add that variables into the model. Okay, so in here we can use the adjusted coefficients to make decision about whether to add more independent variables into the model, and also we use the adjusted R square to compare the goodness of fit between model with different number of independent variables, but they must have the same dependent variables. Okay, so that is um, the role of the adjusted R square. But if you are asked to report the goodness of fit of the sample regression model, you still use the coefficient of determination R square. Okay, the adjusted R square is used just in the case when you want to compare the goodness of fit between different model, and in the case when you consider adding one more independent variables into the model. Okay, all right. When you want to report the goodness of fit of the sample regression model, you still use the coefficient of determination R square. Okay, right. And the relationship between R square and adjusted R square. We have discussed about this already. Now, the general case, okay, the general case, sorry, K plus 1 variables regression model. Wait a minute. Okay, here I have the general case, a K minus 1 variables regression model. We have studied 2 variable regression model. We have studied 3 variable regression model. Okay, and we see that for a 2 variable regression model, we have one dependent variables and one independent variables. For a 3 variable regression model, we have one dependent variables and two independent variables. Okay, so in general, for a k plus 1 variable regression model, we have one dependent variables in the model and k independent variables in the model. Okay, so we always have one dependent variables in the model, and we can have one or more independent variables in the model. Okay, so here is the population regression model for the general case, a k plus 1 variables regression model. Look at this. We have the conditional expected value of y. Okay, the conditional expected value of y, the expected value of y, conditional on the certain value of x1, x2, x3, and so on to xk, okay, is equal to beta 0 plus beta 1 times x1i plus beta 2 times x2i and plus so on and plus beta k times xki. Okay, here we have we have k slopes, okay, beta 1, beta 2, beta 3, so on to beta k, okay, associated with k independent variables in the model. And beta 0 here is the intercept, so we have k plus 1 parameters of this model. Okay, this model has k plus 1 parameters and it has k slopes, okay, and k independent variables. All right, and we can also write the population regression model in the stochastic form. We have the observed value of y is equal to the conditional expected value of y plus ui. Okay, where ui is the disturbance of the model. All right, and the corresponding sample regression model is here. We have the fitted value of y or the estimated value of y here. yi hat is equal to beta 0 hat plus beta 1 hat times x1i plus beta k hat times xki. Okay, and also the stochastic form of the sample regression model for a k plus 1 independent variables. Okay, so is this model a linear regression model? Is this model a linear regression model?
Yes.
Yes. Okay. Yes, it is a linear regression model because all the parameter have the power of 1. All right. So for a linear regression model, how can we estimate the model? How can yeah, we will use the method of OLS. Okay, we use the OLS estimation method to estimate the model, estimate a linear regression model. Okay, we will still use OLS estimation method. The OLS estimation method when identify the sample regression model that minimize the sum of square residuals. Okay, and here we will take, okay, we have here is the sum of square residuals, all right, where residual ui hat is equal to y minus the fitted value of y, okay, where the fitted value of y is equal to this one, all right, and we have to find the sample regression model that minimize this one, which means that we have to solve for the value of beta 0 hat, beta 1 hat, and so on to beta k hat, okay, and here similarly to the two variable regression model, we will take the first derivative of this expression with regard to beta 0 hat, beta 1 hat, beta 2 hat, and so on to beta k hat. We will have a set of equations with k plus 1 equations and k plus 1 roots. Okay, and because the number of equations is equal to the number of roots, we can solve for this set of equations. Okay, we can solve for the root here. Okay, because solving a set of equations like this, a big set of equations like this, will take plenty of time. We will use software like Stata, like eView, like Gretel, or SPSS, and other software, other econometrics software to help us estimate the model. All right. Okay. Now, the basic assumption of the classical linear regression model applied for a multiple regression model. Wait, do you have any questions here first? Any questions here? For the general case.
Cô ơi, cái này bình thường thì sẽ dùng phần mềm hả cô?
Đúng rồi. Với những cái mô hình multiple regression model này thì các bạn sẽ dùng phần mềm nhé, bởi vì tính toán nó rất là phức tạp.
Thế đi thi thì sao?
Đi thi à? Đi thi thì nếu mà có tính toán thì cô sẽ chỉ yêu cầu tính toán cho two variable regression model thôi. Còn với những cái phần multiple regression model này thì chủ yếu là chúng ta sẽ diễn dịch cái kết quả, đúng không ạ? Chúng ta sẽ đọc cái kết quả từ Stata.
Thôi em hiểu, em cảm ơn cô ạ.
Okay. The exercise and questions you will see in the final test will be the same type as the questions and exercise that I asked you in the practice exercise. Okay. For two variable regression model, you may have to calculate the estimated coefficient and the estimated variance of the coefficient. But for multiple linear regression model, you just have to interpret the estimation output from Stata. Okay, will not ask you to calculate the coefficient, the estimated coefficient of multiple linear regression model. Okay, any other questions for the general case? No? All right, so we will move on. All right, the basic assumption of the classical linear regression model applied for multiple linear regression models. All right, so we have discussed the basic assumption of the classical linear regression model in chapter 2, okay? And we also call them the basic assumptions of the OLS estimation method, all right? And we have some assumption like this. The first one, the regression model is linear in the parameters. Okay, we already have this in the basic assumption for the two variable regression model. We also have x value are fixed in repeated sampling, which means the value of x are known or are determined before we bring it into the regression model. Okay, number 3, we have zero mean value of the disturbance UI. We still have that for the multiple linear regression model. Just the only difference here is that the only difference here is that the conditional mean value of y is conditional on the certain value of x1 and x2, okay, and so on to xk, all right, and is equal to 0. Okay, the only difference is here. All right, 4, we have homoscedasticity or equivariance of UI. Okay, it is the same as two variable regression model. The only difference is that it is the conditional variance, and the conditional here is based on certain value of x1, x2, so on to xk. Okay, this one is a constant number, which is sigma square. Okay, sigma square. Sigma. Okay, I have a little, not much room here, which is equal to sigma square. Okay, the only difference is here, the condition. Okay, the condition here is not one independent variables, but based on based on the certain value of all the independent variables in the model. Okay, assumption number 5 is that we have no correlation between the disturbance, the same as in the two variable regression model. All right, number 6 is a new one, and number 7, the model is exactly specified, correctly specified. So number 6 here is about multicollinearity. We have talked about multicollinearity in the previous lecture. We say that multicollinearity is about the correlation between the independent variables of the model. In two variable regression model, we have only one independent variables. That's why we do not have the correlation here that between the independent variables. But for multiple regression model, we have many independent variables into the model. So there will arise the correlation between the independent variables. All right. And as you see, the higher correlation between the independent variables, okay, will cause the estimated coefficient to be less precise. Okay, so here we assume that there is no perfect multicollinearity among the independent variables, so that we can calculate the value of the estimated coefficient. In the case where we have perfect multicollinearity in the model, you will not be able to calculate the value of the OLS estimators. Okay, all right. For assumption number 7, okay, assumption number 7, we have the model is correctly specified, which means that, okay, you can add all the important variables. Okay, you can specify, you can add the important variables into the model to explain for the dependent variables. Okay, and also you have to determine, okay, you have to determine the correct functional form of the model. Okay, determine the correct functional form of the model. All right, so now let's talk about the case when you cannot add all the important variables into the model. Okay, important variable here means the important independent variables which significantly explained for the value of the dependent variables. All right, now do you have any questions here regarding the basic assumptions? All right. If not, we will move to the case where we do not add we do not add all the important variables, the important independent variables into the model to explain for the value of the dependent variables. What will happen to our estimators? What will happen to our OLS estimators? Okay, so what when you think what when you think about the characteristic of the OLS estimators if we do not have all the important variables, important independent variables in the model? What happened to the OLS estimation method when we cannot add important independent variables into the model? What will happen to the OLS estimation method? At OLS estimators, what will happen to them? Are they still the best linear unbiased estimator of the parameters?
I think yes.
Yes? Okay. Remember that when we cannot add the important independent variables into the model, okay, when we cannot add important independent variables into the model to explain for the dependent variable y, what will happen to the OLS estimators of the model? Okay, are they still the best linear unbiased estimators? Are they? Is your answer still yes? Actually, no. Actually, no. Because when we cannot add important independent variables into the model to explain for the dependent variables, okay, the model here is not correctly specified. Okay, the model is not correctly specified, and then the assumptions, one of the assumptions of the OLS estimation method is violated. Okay, one assumption of the classical linear regression model is violated, and then the OLS estimators will not be the best, okay, will no longer be the best estimators of the unknown parameters. All right, because as long as one assumption, any assumption is violated, all right, then the OLS estimation method will no longer be the best linear unbiased estimators of the unknown parameters of the model. Okay, remember that. And also the case if you cannot add important variables into the model, our OLS estimator will not be the best estimator anymore. Right? Let's see the case. Let's see the case. Oops. All right, here. Omitted variable bias, missing important variables. Okay, what will happen if we omit important variables of the model? Okay, so now suppose that, okay, I have an example here to show you the effect of missing important variables. Okay, the consequence of missing important variables. So suppose that the right model is like this, is model 1. Here we have yi is explained by the independent variable x1 and independent variable x2. Okay, so suppose that this one is the correct model. Okay, but then the corresponding sample regression model will be here. All right, and this one, beta 1 hat here, is the estimated, okay, is the estimated coefficient, and it will estimate, okay, it estimate how the independent variable x affect the dependent variable y. Okay, this one is the estimated effect. All right, beta 1 here show the effect of x1 on y, okay, and beta 1 hat here is the unbiased, okay, is the best linear unbiased estimators of beta 1, which means that is a unbiased estimate, effect of x on y. Okay, because this model is the correct model and it satisfies all the basic assumption of the classical linear regression model, then beta 1 here, beta 1 hat here is the unbiased, the best unbiased, okay, estimated effect of x on y. All right, okay, but when we specified, okay, the population regression model, we do not bring x2 into the model. So our model here, the model that we construct here, is not the same as the correct model. Okay, maybe because we do not know the value of we do not know of the effect of x2 on y, or maybe we do not have the data of x2, for example. That's why we will construct a model that we use x1 only to explain for the value of y, and we have model 2 like this. Yi here is equal to alpha 0 plus alpha 1 times x1i and plus u2i here. Okay, this one is model 2 and this one is the correct model, model 1. Okay, so the corresponding estimated model of the model 2 will be like this. We have yi hat here equal alpha 0 hat plus alpha 1 hat times x1, and alpha 1 hat here, okay, alpha 1 hat here is the estimated effect of x1 on y, okay, estimated by this model. Okay, alpha 1 here, alpha 1 hat here is the effect of x1 on y estimated by this model. Okay, by this model. So is alpha 1 hat the same as beta 1 hat here? Remember that beta 1 hat here is the unbiased estimators, okay, is the unbiased estimated effect of x1 on y. Okay, so if alpha 1 hat here equal beta 1 hat, okay, so alpha 1 hat will be the best unbiased estimated value of beta 1, okay, of the effect of x1 on y. But if not, alpha 1 hat here will not be the unbiased, will no longer be the unbiased estimate of the effect of x1 on y. All right. Now let's see whether alpha 1 hat is the same as beta 1 hat. All right. Now, in order to answer these questions, we will regress x2 on x1. Okay, we regress x2 on x1 and we get this model. Okay, we have x2i equal sigma 0 hat plus sigma 1 hat times x1i. Okay, that is what we obtain when we regress x2 on x1. Okay, now replace this one into the right estimated model. Okay, we have yi hat here is equal to beta 0 hat plus beta 1 hat times x1i plus beta 2 hat times what? Okay, sigma 0 hat plus sigma 1 hat times x1 here, okay, which is x2, this one, x2 here. Okay, now we will have yi hat here equal beta 0 hat plus beta 2 hat times sigma 0 hat. We put it here, okay, and we have beta 1 hat plus beta 2 hat, okay, beta 1 hat plus beta 2 hat times sigma 1 hat, okay, and multiply by x1i, okay. So here we have the estimated model with one independent variable, that is x1, okay, and this one, okay, beta 0 hat plus beta 2 hat times sigma 0 hat. This one is equal to our alpha 0 here, okay, equal to alpha 0, and alpha 1 hat is equal to this one, okay, alpha 1 hat, alpha 1 hat is equal to this one, beta 1 hat plus beta 2 hat times sigma 1 hat. Okay, so obviously you can see that alpha 1 hat is different from beta 1 hat. Okay, alpha 1 hat is different from beta 1 hat because we have one more add-on here. Okay, beta 2 hat times sigma 1 hat. All right. Okay, so it means that alpha 1 hat is a bias estimator of beta 1. Okay, beta 1 alpha 1 hat is a bias estimator of beta 1, the correct effect of x1 on y. Okay, now let's see the case. For example, if we have okay, if what? Okay, so if beta 2 hat, wait a minute, if beta 2 hat I make the case more clear here. If beta 2 hat is greater than 0, okay, let's see the case when beta 2 hat is greater than 0. And if x1 and x2 are positively correlated. Now I make some mistake here in writing the slide. So if you are using my slide, the slide that I sent you, please make the correction, yeah, accordingly. Oops. Wait a minute. Okay. All right. So if beta 2 hat is greater than 0, which means that x2 has positive effect on y, okay? And in the case if x1 and x2 are positively corrected, alpha 1 is an upward estimator of beta 0, beta 1, which means that alpha 1 hat is usually, okay, the expected value of alpha 1 hat is greater than beta 1, okay? And if x1 and x2 are negatively correlated, then then alpha 1 hat will be a downward estimators of beta 1, which means that the expected value of alpha 1 hat is smaller than the actual value of beta 1, okay? All right. And you can infer for the case when beta 2 hat is smaller than 0. Okay, for the case when beta 2 hat is less than 0, you can see that if x1 and x2 are positively correlated, then alpha 1 is a downward estimators of beta 1. Okay, and if for the case when beta 2 hat is less than 0 and x1 and x2 are negatively correlated, then alpha 1 hat will be an upward estimator of beta 1, which means that the uh, expected value of alpha 1 hat is greater than the actual value of beta 1. Okay, and also we can prove that the estimated variance of alpha 1 hat, which means that the estimated and the standard error of the estimated coefficient va of the beta hat, okay, variance of the beta hat or the standard error of the beta hat will also be biased. Okay, so in the case, you can see that in the case where we omit important independent variables of the model, the OLS estimator will be biased estimator, which means that it is no longer the best estimators for our unknown parameters. Okay, so remember when you specify the population regression model, please use the theories, okay? Please use the economic theories of previous researchers to find, okay, to determine the important independent variables of the model and try to not omit them from your model, all right? Otherwise, the estimated model or the estimated value that you get for the unknown parameters will be unbiased. All right, they will be no longer the best estimators for the OLS for the unknown parameters of the model anymore. All right, okay, that is the problems of missing important independent variables of the models. Okay, understand? Any questions here? Do you have any questions here? No? Okay, good. Let's move on. All right, so we have just talked about specify important, okay, determine important variables of the model. There's another things about the correct specification of the model, that is the correct functional form of the model. Okay, not only do we have to bring into important independent variables, okay, we also have to identify we have to determine the correct functional form of the model, whether our model has a linear functional form, or it has a quadratic functional form, or cubic functional form, or something like that. Okay, we have to determine the correct functional form of the model. Okay, and how can we determine the correct functional form of the model? It depends on the theories, it depends on previous researches, and it depends on our hypothesis. All right, now, so for previous model that we have discussed about, we just talk about model that show a linear relationship between the independent variables and the dependent variables. Okay, now make it clear that we are not talking about linear regression model. We are talking about linear relationship between the dependent variables and the independent variables. Okay, so for example, we have uh, we have been talking about multiple two variable regression model where we have yi is equal to beta 0 plus beta 1 times xi plus ui. We also talk about k plus 1 variable regression model where we have yi equal beta 0 plus beta 1 times x1i plus beta 2 times x2i and plus so on to beta k, right, plus beta k times xk and plus ui. Okay, all of these models shows a linear relationship between the dependent variable y and the independent variable x. Okay, for this one, we also see a linear relationship between y and x1, a linear relationship between y and x2, and a linear relationship between y and xk. Okay, so all of the models that we have discussed show a linear relationship between x and y, between the independent variables and the dependent variables. Well, okay, but in reality, okay, in economics, we do not only have the linear relationship between variables. Okay, we also have non-linear relationship between the variables. Okay, for example, the relationship between the average cost, okay, the average cost and the number of products produced, okay, and the number of products, okay, as long, okay, you can see that the average cost, okay, when we increase the number of products, the average cost per each products will decrease, right? The average cost will decrease, but at first it decreased with a very high at a very high rate, but gradually the rate will decrease. So you can see that here, if we have, here is the average cost and here is the number of products. Okay, here's the number of products. Then the average cost at first will drop significantly, but the rate of change will gradually decrease. Okay, like this. All right, so the relationship between average cost and the number of products is not a linear regression model. Okay, so if you still use this type of model to estimate the relationship between products and average cost, your estimate will be wrong. Okay, your estimate will be not a correct estimate. All right, so you can see that there are different functional forms Okay, there are different functional form of our population regression model. How we determine, okay, how we determine the way that we determine the functional form of the population regression model depends on the theories and depends on previous researchers. All right, okay, so we let's see what are the nonlinear relationship, what can be the nonlinear relationship between the independent and dependent variables. All right, okay, here look at the slide. Look at the slide we have here. All right, you can see that we have the graph of different functional form. So if y is a cubic functions of x, then the graph of y will be like this or like this. Okay, this is the graph of y. Okay, if y is a cubic function of x. This one, if y is a reciprocal functions of x, then the graph of y will be like this. Okay, if we have log model, which means that y and x do not have a linear regression, a linear relationship. This is a log. If we have log, the natural logarithm of y is a function of the natural logarithm of x. The graph of x and y will be look like this. Okay, will look like this. This is the case. Okay, also log model. If we have the slope is smaller than 0, this is the case where the slope is greater than 0. Okay. Here is the case where we have the natural logarithm of y is a linear function of x. Okay, and here's the case where we have y is a function of the natural logarithm of x. Okay, so based on the graph, you can see that between variables, we have many other nonlinear regression, nonlinear relationship between the variables. Okay, so for economic variables, there can also be many other nonlinear relationship between them. Okay, so our population regression model will have other functional form, okay, rather than just the linear relationship between x and y. All right, now we will talk about the linear relationship between x and y after the break. Okay, let's take a 20-minute break and then we will come back and talk about the non-linear relationship between x and y. All right, okay, let's take the break.
Cô ơi, lát cô gửi lại cái slide này lên file được không cô?
Cô có gửi rồi mà.
Tức là cô có sửa một số chỗ mà cái slide cô gửi ở trên đấy nó lại không edit được ạ. Nó là file ảnh ạ.
Ok, ok, cô sẽ gửi lại. Nhớ nhắc cô nhé.
Dạ vâng ạ.
Chạy có xuống cho ăn luôn nên là
Okay, have you come back yet? Hello?
Yes.
Yes.
Okay, all right, so let's continue. All right, let's talk about the nonlinear relationship between the dependent and independent variables. All right, we will talk about some some common nonlinear relationship between the independent and dependent variables. The first one is the log-log model. Okay, so here, although we are talking about the log, usually in mathematics, you see log here as the logarithm to the base of 10. Okay, but in economics and econometrics, we do not use the logarithms to the base of 10s. Okay, we use the logarithms to the base of e, which is the natural logarithms of any number, or the natural log of any number. Okay, so log here, although we are using log model, we are talking about the natural log of the number. All right, so that's why we can see here the log model has the following functional form. We have the natural log of y is equal to beta 0 plus beta 1 times the natural log of x and plus ui. Okay, and this one, in this case, beta 1 is the slope. Just wait a minute. Okay, beta 1 here is the slope, and it tells us, okay, when the natural log of x increase by 1 unit, okay, then the natural log of y will increase by beta 1 unit on average. Okay, but we do not want to talk about the relationship between the natural log of x and the natural log of y. We want to talk about the relationship between x and y, how x affect the value of y. Okay, then we will talk the okay, when from the statement, okay, the when the natural log of x increase by 1 unit, then the natural log of y will increase by beta 1 unit. It is equivalent. It is equivalent to when x increase by 1%. Okay, then y will also increase by beta 1% on average. Okay, this just makes some mathematics transformation. You will get the equivalent statement. All right, beta 1 here, the slope, will tell us about the relationship between x and y. That is, when x increase by 1%, then then y will increase by beta 1% on average. Okay, and remember that because x here is not in a linear form. Okay, x is not in the linear form. X is in the form of a natural logarithm. Then the change with x will be the percentage change. Okay, y here is also not in the linear form. Y is in the form of a natural log. Okay, and then the change in y will also be percentage change. Okay, remember that. Beside log model, we have semi-log, okay, semi-logarithm model. We have the natural log of y is equal to beta 0 plus beta 1 times x plus ui. This one is called a log linear model. Okay, this one is called a log linear model. All right. And also we have another semi-log model, which is yi equal beta 0 plus beta 1 times the natural log of x plus ui. This one is called the linear log model. Okay. These two models are semi-log model. But the first one here is a log linear model, and the second one is a linear log model. And the interpretations of the slope will be different between these two models. For the first one, for the log linear model, beta 1 here show that when x increase by 1 unit, okay, then the natural log of y will increase by beta 1 unit. But we don't want to know the relationship between x and the natural log of y. We want to know the relationship between x and y. Okay, so the relationship between x and y here will be when x increased by 1 unit. All right, the dependent variable y will increase by beta 1 times 100%. Okay, on average. Okay, that is the meaning of the interpretation of the slope here. And for the second model, that is the linear log model. Okay, beta 1 here tells us that when the natural log of x increase by 1 unit, okay, then y will increase by beta 1 unit on average. Okay, now let's change into the relationship. Okay, turn it into the relationship between x and y. Okay, when we talk about the relationship between x and y, beta 1 here will tells us that when x increase by 1%, okay, when x here increase by 1%, then the dependent variable y will increase by beta 1 divided by 100 units. All right. Why do we have beta 1 times 100? Why do we have beta 1 divided by 100 here? It is just mathematical transformation. You just do the mathematical transformation, you will get the result. All right. Okay. But one thing we have to note here, okay, if our variables is in the natural log form, okay, if the variable is in the natural log form, then the change in it will be measured in percentage. Okay, each change will be percentage change. And if the variables is in the linear form, okay, if the variables is in the linear form, then the change in it will be in unit. Okay, it means that the linear variables here will have a unit change. Okay, all right, and remember that for the interpretations of log linear is different from the interpretation of the slope of a linear log model. Okay, one is beta 1 times 100%, and one is beta 1 divided by 100 units, right? Okay, we have some very common nonlinear relationship model, that is the polynomial model, where we can have a quadratic forms, which means that y is a quadratic functions of the x, or y can also be a cubic function of x. Okay, for example, here we have y is a quadratic function of x, where we have yi is explained not only x, but also the square of x. Okay, we have yi is equals beta 0 plus beta 1 times x plus beta 2 times x squared and plus ui. This model has two independent variables, which is x and the square of x. Okay, and those polynomial like quadratic model or cubic model will allow you to display, okay, it allow you to display the diminishing or increasing marginal effect of the independent variables on the independent variables. Okay, all right. Now, uh, what we care about here, you can see that for linear relationship between x and y, okay, we say that when x increase by 1 unit, when x increase by 1 unit, y will increase by beta 1 unit. Okay, so the rate of change in x in y corresponding to 1 unit of change in x is a constant. Okay, when x increase by 1 unit, y will always increase by beta 1 unit on average. But for nonlinear relationship, the rate of change of y, okay, is not a constant number. Okay, or we can say in other words, the marginal effects of x on y is not a constant. So let's see that in this slide. Okay, the marginal effect of x on y, which is the first derivative of y with regard to x. Okay, look at this. For a linear regression, a linear functional form, okay, for a model with linear functional form like this, you can see that the marginal effect of x on y, which is the first derivative of y with regard to x, is beta 1, which is a constant number. Okay, so the marginal effect of x on y is not changing. Okay, but for other nonlinear functional form like quadratic, cubic, reciprocal, log-log, or semi-log models, you can see that the marginal effect of x on y here depends on the value of x or y. Okay, for example, this one, for quadratic model, you can see that the marginal effect of x on y here is beta 1 plus 2 times beta 2 and times x. Okay, so the marginal effect of x and y depends on the value of x. Okay, all right, and in this case, the marginal effect of x and y will be a decreasing or diminishing marginal effect if beta 2 here is a negative number. So if beta 2 is a negative number, when x increase, the marginal effect will decrease. Okay, so if beta 2 here has a negative sign, is a negative number, then the marginal effect of x on y is a diminishing one or a decreasing one. If beta 2 here is a positive number, okay, I will move. Wait a minute. Okay, let's continue. All right. For the case when we have a cubic functional form, all right, when we have a cubic functional form like this, the marginal effect of x on y, okay, will be a quadratic functions. So here you can show a marginal effect that at first increasing, then decreasing. You can also show use this model to demonstrate the marginal effect of x and y that at first increase then decrease. Okay, follow the graph of a cubic of a quadratic function. Okay, and also we have other marginal effect of x and y here for a log-log model. The marginal effect of x and y depends on the value of both x and y, like this. Okay, for a log linear model, the marginal effect of x and y depends on the value of y. And for a linear log model, the marginal effect of x and y, x on y depends on the value of x. Okay, so you can see that the marginal effect of x and y is changing for nonlinear regression model. Okay, it is constant for only the linear functional form. Okay, so let's take some example to see the example of our nonlinear functional form. The first one, let's talk about the calculus function in microeconomics. So in microeconomics, you have get used to the calculus production function, where we have the output or the production is exponential functions of the input, like a label or capitals. Okay, and this is the form. Okay, this is the form of the calculus production function. If we put the function like this, if we leave the function like this, it will be hard for us to explain the effect of x1 here, a label on the output, or explain the effect of capital on output. Okay, if we leave the function in this original form like this, it will be hard for us to analyze the effect of each input in the dependent variables, that is the output of the production level. Now, in order to make it easier to analyze this relationship, we will take the logarithm forms of this function, which means that we take the natural log of these equations. Okay, we will have the natural log of y is equal to the natural log of these products. Okay, and which is equal to the sum of the natural log of beta 0 plus beta 1 times the natural log of x1i plus beta 2 times the natural log of x2i and plus ui. Okay, and in this case, it will be easier for us to assess the effect of label or capital on the level of output. Okay, for example, what does it tell us about the relationship between x1 label and y, the level of output for this model? What is the relationship between label and output?
It means that if we use for every 1 unit of output, we will use beta 1 unit of label force.
Mm, uh, actually, it's not like this. Can you repeat? Actually, uh,
I mean that like for every single output we can produce, we will have to use beta 1% of label input.
it's not
Like
like
beta.
It's not like that. Beta 1 here shows us the effect of label on output. Okay, so like what we have in the previous slide. Okay, beta 1 here is a log-log model. Okay, for the log-log model, the slope here will indicate that when x increase by 1%, then the average of corresponding y will increase by beta 1%. So in this case, for the Cobb-Douglas production function, the log form of the Cobb-Douglas production function, x1, if x1 is the label and y is the output, okay, beta 1 here will tell us that when we increase, okay, will tell us about the effect of label on output, which is that when we increase label by 1%, okay, when we increase label by 1% and keep capital unchanged, okay, then the average of y will increase by beta 1%, okay? And the same for beta 2. When we increase capital by 1%, okay, then when we increase capital by 1% and keep label unchanged, y will increase by beta 2% on average. So the change of x and y here is the not the absolute change, but it is the what is it? Relative change. It is relative change, not the the absolute change in the value of x and y. Okay. Do you got it? It is a little bit different from your interpretation. You got it?
Yes.
Yeah. Do you have any questions here? And
Cô nói là nó là không phải tuyệt đối là nghĩa là như nào không?
tức là nhá, ở đây khi mà chúng ta nói là giống như vừa nãy cái giải thích của chúng ta nhé, tức là x mà tăng lên 1% thì y nó sẽ thay đổi trung bình là beta 1%, đúng không ạ? Vậy thì cái sự thay đổi ở x và y ở đây nó là cái sự thay đổi tương đối, thay đổi về phần trăm thôi, chứ nó không phải là cái sự thay đổi về tuyệt đối trong giá trị của x và y, là thay đổi theo đơn vị, đúng không ạ? Absolute change là cái sự thay đổi theo đơn vị, còn cái relative change là cái sự thay đổi theo phần trăm. Được chưa?
Rồi em cảm ơn cô.
Okay. Any questions here? And in researches, in various researches, when we want to investigate the effect of different factors on the production, on the performance of enterprises, or on the performance of an economy, okay, usually we use this function, we use this model as the base model to estimate, okay, to estimate the level of production or the level of the performance of an enterprise or countries. Yeah, this one is the base model, or we can say that label and capital are the important variables that we can use to explain the value of output. Okay, if we want to investigate other factors on output, for example, the effect of what, of green investing, the effect of green investing on the output or performance of enterprises, we still have to put label and capital in the model to explain for the performance beside our interested factor, which is the green investing. Okay, and you can usually we use the log model here, the log model here, to assess the effect of input, like output, like a label, capital, technology, green investing, what environment protection, and so on the performance of enterprises. Okay. Ví dụ mà sau này các bạn có làm nghiên cứu hay là các bạn làm tiểu luận chẳng hạn, đúng không ạ? Và chúng ta muốn tìm hiểu ảnh hưởng của một số các cái yếu tố nào đó, đúng không ạ? Ảnh hưởng của một cái yếu tố nào đó lên cái performance of enterprises hoặc là của một cái của các cái countries, đúng không ạ? Thì chúng ta vẫn có thể sử dụng cái mô hình này là cái base, và sau đó chúng ta ép thêm các cái biến mà chúng ta quan tâm vào, đúng không ạ? Và chúng ta cũng không thể thiếu được, đúng không ạ? Mặc dù là ví dụ như là tôi quan tâm đến cái ảnh hưởng của green investing lên cái performance của enterprises, nhưng mà tôi vẫn không thể thiếu các cái biến như là label hay là capital hay là technology được, đúng không ạ? Bởi vì đó nó là những cái yếu tố cơ bản, những cái yếu tố quan trọng, significantly impact the value of output hoặc là performance of enterprises. Được chưa? Đó. Thì đây là here's an example of the log model. Okay, and how we interpret the slope, the estimated slope of the model. All right, now let's move to another form of nonlinear relationship, that is the quadratic form specifications. Okay, for polynomial form, okay, we can have quadratic, we usually have quadratic and cubic functions. Okay, here we just take the example of quadratic function, and the interpretation of cubic function will be somehow the same. Okay, you can do that if you know how we interpret quadratic function. Now, example. Here we want to investigate the effect of advertising expenditures on the sale of a product. Okay, so for example, we use a linear regression function like this. Okay, so the linear relationship between advertising expenditures and sale, where we have S, the revenues on a product, is equal to beta 0 plus beta 1 times P, which is the price of that good, and plus beta 2 times A, which is the advertising expenditures for that product, and plus UI. Okay, this function is the population regression model that shows the linear relationship between advertising and sales. Okay, so for example, if we have data for this, for revenue, price, and advertising expenditures, okay, we can get the estimated model. Okay, assume that we have available data, then we can use the available data to get the estimated model, which is here. We have the estimated value of sale, the estimated revenue is equal to 118.91 minus 7.9 times P plus 1.86 times A. Okay, so what does the estimated model tells us about the effect of advertising expenditures on sale?
When we increase advertisement by 1 unit and keep other variables constant, the revenue will increase by 1.86 units.
Okay, all right, thank you. So here for this model, for this estimated model, it tells us that when we increase the advertising expenditure by 1 unit, which is $1,000, okay, and keep the price unchanged, okay, the revenue will increase by 1.86 unit, which is $1,860 on average. Okay, so it means that when we increase advertising expenditures, okay, as long as we increase the advertising expenditures, the sale will increase at that constant rate, which is 1.86 unit per unit change in advertising expenditures. So is true. Do see that in reality.
No, because it will fall off until it reaches near zero.
Yeah, right. Yeah, actually, the effect of advertising expenditures on sale is a decreasing marginal effect. Okay, it's a decreasing effect. So when we increase, okay, the level of advertising expenditures, so the marginal effect of expenditure on sale will decrease. Okay, so this model cannot show that relationship, cannot express that diminishing marginal effect of advertising expenditure on sale. Okay, so if we believe that the marginal effect of advertising expenditures on sale is decreasing, okay, not a constant number, then we cannot use this model to estimate the relationship between advertising expenditure on sale. Okay, and in that case, you have to use a model that show a nonlinear relationship between advertising expenditure and sale. And here, to demonstrate, to show the diminishing, to test the diminishing marginal effect of advertising on sale, we can use a quadratic model between sale and the advertising expenditures. So here we have sale as the revenues is equal beta 0 plus beta 1 times pi plus beta 2 times a and plus beta 3 times a square and plus ui. Okay, and let's see what is the marginal effect of advertising on sale for this model. For this model, the effect of change in advertising expenditure on sale is like this. We take the derivative of sale with regard to advertising expenditure, and we get this value. Beta 2 plus 2 times beta 3 and times AI. Okay, so the marginal effect of advertising expenditure on sale depends on the level of expenditures of advertising expenditure that has been has been used, that has been spent. Okay, all right. So let's see if we still use the available data that we use to estimate the first model. Okay, we will obtain the following estimated model for the second one. We have the estimated sale here is equal to 109.72 minus 7.62 times P and plus 12.15 times A and minus 2.777 times A squared. Okay, and for the estimated model, okay, for this estimated model, you can see that the marginal effect of advertising on sale here is what we have 12.15 minus 2 times 2.77 times A. Okay, and you can see that the marginal effect of advertising on sale is largest when we are not investing anything in advertising expenditures. Okay, which means that when the level that we spend, when the level of advertising expenditures is equal to zero, that means that we are not investing anything in investment. So the marginal effect of one additional change in the advertising expenditure is the largest. Okay, and that marginal effect will decrease when I increase. when the level of advertising expenditure increase, the marginal effect of one additional unit of advertising expenditure on sale will decrease. Okay, and we should stop investing in advertising expenditures when we have the marginal benefit of advertising is equal to the marginal cost of advertising. Okay, so what is the marginal benefit of advertising? In this case, what is the marginal effect? We say that when the marginal benefit is equal to the marginal cost, we have the optimum level. Okay, we have the optimal level of advertising. Okay, like we have optimal production level. Okay, so here we have the optimal level of advertising if the marginal benefit of advertising is equal to the marginal effect as a marginal cost of advertising. So what is the marginal benefit of advertising here? What is the marginal effect of advertising? Can you just tell us what is the marginal benefit of advertising?
Minus 2 times 2.77.
Yeah, so the marginal benefit of advertising here is the effect of one additional increase in advertising expenditures on sale, which is the increase in sale, okay? Which is the increase in sale with regard to one additional increase in advertising expenditure, one additional unit, additional unit increase in the level of advertising expenditures, okay, which is the first derivative, this one, which is the first derivative of sale with regard to advertising expenditure. This is the marginal effect, the marginal benefit of increasing one additional unit of change in advertising expenditures. Okay, now what is the marginal cost of that? What is the marginal cost of increasing one additional unit of advertising expenditures? What is the cost of that? The marginal cost here, what is the cost of increasing one additional unit increase in advertising expenditures? What is it? It is just the money that we spend for that one additional increase in advertising expenditure, which is 1,000, right? 1,000, one unit of advertising expenditure. That is the marginal cost here. When we increase, okay, when we increase the level of advertising expenditure, the cost here is the money that we spend for that. Okay, so it is one unit increase in the level of advertising expenditures. Okay, so based on that, what is our optimal level of advertising expenditures? What is our optimal level of advertising expenditures in this example?
When s equal to 0, so we can calculate.
When s equal to 0?
Yeah, so that we can calculate we can calculate a advertising expenditure is optimal to maximize S.
Now, optimal level is not the maximum level. Okay, optimal level is different from the level that maximize the what maximize the revenue that we get. Optimal level is different from the maximum level. Nào, cái level, cái optimal level của advertising nhá, thì nó khác với cái level của advertising mà maximize revenue. Đúng không ạ? Các bạn học microeconomics rồi. Cái optimum level thì nó khác với cái level mà nó maximize cái revenue của chúng ta. Đúng không ạ? Ở đây cô muốn hỏi là cái optimum level of advertising expenditure chúng ta sẽ có được khi nào? Đúng không ạ? Rồi, ở trong microeconomics thì chúng ta có là cái maximum level, cái optimal level chúng ta sẽ đạt được khi mà cái marginal benefit nó bằng với marginal cost. Đúng không ạ? Rồi, ở trong cái trường hợp này thì marginal benefit của chúng ta chính là cái sự thay đổi, đúng không ạ? Cái sự thay đổi ở trong sale ứng với một đơn vị thay đổi ở trong advertising expenditures. Đúng không ạ? Tức là chính là cái thằng này đấy. Chính là cái thằng này. Đúng không ạ? Chính là thằng này. Thế còn cái marginal cost của chúng ta là gì? Marginal cost ở đây là cái số tiền mà chúng ta bỏ thêm cho một đơn vị quảng cáo. Đúng không ạ? Cái số tiền chúng ta bỏ thêm cho một đơn vị quảng cáo. Ở đây chính là một unit của advertising expenditures. Đúng không ạ? Vậy thì cái optimum level của advertising expenditure đạt được khi nào ạ? Khi mà cái thằng này, đúng không ạ? Khi mà cái marginal benefit này bằng với cái marginal cost là 1 ở đây. Đúng không ạ? Thì các bạn chỉ việc ghép hai cái thằng này bằng nhau thôi. Đúng không ạ? Các bạn sẽ tính ra được cái optimum level of advertising expenditures. Thấy chưa? So here is the marginal benefit. This one is the marginal benefit of increasing one additional unit of advertising expenditures. Okay, and this one is the marginal cost of increasing one unit of advertising expenditures. So we will get the optimum value, we will get the optimum level of advertising, okay, when the marginal benefit equal the marginal cost, which is this one, equal to 1. Okay, now please help me to calculate the level of A that that will give us the optimal situation. What is it? What is the value of I here? Okay, so the optimum level of advertising expenditure is achieved when the marginal benefit, which is this one, is equal to the marginal cost, which is 1. Okay, and so A here will be 12.15 minus 1 and divided by 2 times 2.77. And what is the value?
2.0126.
26. Okay, so this one is the optimum level of advertising. Okay, optimal value, optimal level of advertising. Okay, that maximize our benefit. Okay, the optimum level will achieve when the marginal benefit is equal to the marginal cost. Any questions here? Any questions? Or do you don't understand anything? Do you not understand anything? No? Okay, good. Then we have done with the multiple regression model. Okay, we are done with the multiple regression model. Now, please, for your group work, please find more independent variables to explain for your dependent variables and estimate that multiple regression model. And what is the new coefficient of determination of your model? Okay, explain it. Does the new added variables explain a lot more for your dependent variables? Okay, that is for your group work. Find more independent variables to explain for your dependent variables. Okay, and estimate the model. All right. And remember to show your reasoning. Okay, remember to explain why you choose those independent variables to bring into the model. Okay. All right. Do you have any questions regarding today's lecture? No? Okay. So our lecture ends here. See you on see you on Friday, and on Friday we will study a new chapter, which is chapter 4. Okay, we will do hypothesis testing and forecast from the estimated model. All right. Oh, please remind me to upload the new slide for chapter 4. Okay. Okay. Goodbye, student. See you on Friday.
Bye, teacher.
Bye bye.
Chào cô ạ.
Ok, chào các bạn. Bye. Yeah, bye bye.